In this video, we look at an application of Fourier series, and we see if we can compute the deflection of a beam using Fourier series. We consider a simply supported beam with load P, properties EI, length L. We know that the exact deflected shape of this beam is given by this equation, which we can find in any standard structural analysis book, or we can also obtain by simply solving the differential equation exactly. But let's see if we can compute an approximate solution using Fourier series. And then we can compare this with the known exact solution. The Fourier series we developed in the previous video is not ideal for this application because, number one, the constant and cosine basis functions don't satisfy the boundary conditions. Second, the sine basis functions force the displacement to be zero in the middle, and we know that the displacement isn't zero at the middle. So although these basis functions could be used, they're not ideal. We'd like to see if there are basis functions that they're orthogonal again, but they satisfy the boundary conditions. So we consider these other functions: sine that makes half a cycle over the length L, sine that makes 1.5 cycles over the length L, a sine that makes 2.5 cycles, 3.5 cycles, and so on, but they're all multiplied by square root of 2 over L, again, so that when dotted with themselves, they give 1. So our Fourier series, in terms of these sine functions, can be written as an times square root of 2 over L times the sine that makes half, 1.5, 2.5 cycles over the length 0 to L. The differential equation for bending of the beam is d to the power of 4u by dx to the power of 4 is p equals p over ei. So if we substitute our Fourier series into the differential equation and compute the fourth derivative of u, we get this. Now, to compute the coefficients an, we have to dot both sides with the corresponding basis sine function. So to compute, let's say, the mth coefficient, we dot both sides with square root of 2 over L times sine 2 times m minus 1 pi x over L. And if we do that integral, we get this. So from this, we can compute am equals 2p over ei times the square root of 2 over L times the quantity L divided by 2m minus 1 pi, the whole to the power of 5. So if we substitute this back into the Fourier series for u, and then cancel out some common terms and also normalize the displacement by pl to the power of 4 over ei, then we get this. Notice that in the denominator we have 2n minus 1 pi raised to the power of 4, and you see how quickly that goes to 0 as a function of n. Now, to see how this Fourier series converges to the exact displaced shape that we know, look at the MATLAB live script that's provided with this video. Now, it seems like we kind of made up these basis functions, but there's a systematic way of constructing basis functions that satisfy appropriate boundary conditions by solving a symmetric operator with the appropriate boundary conditions in the region of interest. That's just a note. We'll not get into that too much further in this assignment.